in terms of an agenda this evening, we're going to dive into like what a confidence interval quite literally is. We will define a point estimate, a margin of error, learn how to calculate margins of error for proportions, as well as run a simulation where we'll actually create some confidence intervals and see what happens when we change the sample size, what happens when we change the confidence level, and make sure we know all the different ins and outs of what a confidence interval represents. And then we'll actually dive into the specific nitty-gritty of calculating. So we'll do both some multiple choice and free response practice. It looks like I might have a couple of people here with me live. If you're watching on replay, of course, use the timestamps on the side to jump ahead and get what you need. But if you are here live, please ask questions, put comments in the chat, answer stuff if it comes up. Otherwise, I'm going to be pretending to be teaching a blank screen, and I would love to interact with some folks who are here if you are indeed here. Before we dive into some specifics with confidence intervals, big picture, the second half of AP statistics is all about what's called inference or inferential statistics. And really at its core, the big goal of inference is to gather information about a population by using a sample. And that statistic we get from our sample will provide the basis for estimating an unknown population parameter. So depending on what kind of scenario you're looking at, the statistic might be different from case to case. If you're working with a categorical variable, you're probably going to be calculating a proportion. If you're working with a quantitative variable, you'll probably be calculating a mean. And the symbols on your screen hopefully are familiar to you now at this point. This evening, we're going to be specifically focused on that left column of proportions, and we'll work with means next week. So we'll be building confidence intervals to estimate unknown population proportions from a sample p-hat or sample statistic. And there are two main tools of inference. So when you get to the free response section, and you're guaranteed to see each of these things at least once in the 6 questions, and that is to do something with a confidence interval, which is a way to create a range of what are called plausible values for an unknown parameter. So come up with a good set of guesses for what the population proportion or population mean is. And you can also run a hypothesis test, which is when someone tells you what P or mu is, and you have to take a sample to decide whether or not you agree with them, whether you're going to reject or not reject that null hypothesis or that claim about the parameter. We're not doing hypothesis tests this week. We're focusing specifically on confidence intervals, but hopefully we're at the point in the school year where you're probably getting into some of these, if not both of these at this point. And please, if you're here live, definitely share what you have and haven't done yet, just so I can make sure I tailor explanations to the folks who are here. But both of these things follow a similar format when it comes to inference. First, you have to identify what you're trying to estimate or investigate. So what parameter are we looking at? Is it a categorical situation where I'm estimating P? Is it a quantitative situation where I'm estimating mu? Then figure out if the conditions to do the inference are met. We'll talk more about conditions later, but typically those are taking random samples and having big enough samples. And there are some magic numbers involved for both of the different cases. We'll then actually take a sample or two and do some calculations. And then based on the calculations that we do, we'll make a conclusion, whether that is saying we believe that the actual proportion is between here and here, or I have enough evidence to reject this hypothesis and go with this alternative of this other thing instead. And again, tonight we're going to specifically jump into confidence intervals. But if your teacher talks about inference, they're probably referencing one of these two things: building a confidence interval or running a hypothesis test. And so let's dive in. Again, if you are here live, please do put in the chat so I can see kind of your familiarity level with confidence intervals. If it's something that were already through that unit, I've done this already, or haven't started. Okay, we just finished hypothesis test and are starting chapter 10. So Dara, it sounds like you've specifically done one sample intervals and one sample tests. That's good, because this should be a good review for you in that case. And at the end, we can definitely do a couple of like 2 sample comparisons and see some examples of that. So hopefully this will jog your memory, because a confidence interval at its most basic thing is, going to come off of these kinds of statements. So you might have seen these. I mean, if you're reading newspapers or reading, things online, you'll see like in 2017, 89% of teenagers reported having a smartphone, or the average American adult spends 4 hours watching TV per day, or 63% of registered voters say they plan to vote for candidate A. The margin of error is plus or minus 3%. Okay, those numbers in bold, they had to come from somewhere. And there is no actual survey that actually can talk to every single teenager in the country, or every single American adult, or every single registered voter. So all of those numbers are really estimates. They're really statistics that are meant to represent an entire population. And so we got to ask ourselves, how can we be sure they're accurate? What the heck is a margin of error? And that brings us to the first part of a confidence interval. Okay, cool. You're looking for review. Yeah. Okay. Well, hopefully you'll be really on board with confidence intervals. I will tell you hypothesis testing. We're going to get into that in a couple of weeks. So if you do find that this is, not up your alley tonight, look at the schedule coming up and, feel free to come in and out. But this will be some good review of confidence intervals for you, hopefully. And so back to the folks who are watching on replay, a confidence interval is made up of two things. Okay. And the first thing is called a point estimate. So those numbers in bold you read were single numbers that estimated something about an entire population, and they are called point estimates. So in the case of proportions, your p-hat is a point estimate. So if you find in your survey that 89% of teenagers say this thing, then your best guess for what all teenagers are doing is 89%. But as we know from lots of experiences here, statistics vary from sample to sample due to randomness, due to variance, due to potential sources of bias, which hopefully we don't have in our sample. And so we really can't be sure that the point estimate is the correct value of the parameter. And so that's where the margin of error comes in. Yay, margin of error. And that's this idea of giving ourselves some wiggle room to say 89%, okay, it's a good guess, but is it really the answer? Let me give myself some room on either side to figure out if I can, give a range of guesses that all could be realistic given the data I have in front of me. And so at its most basic form, this is a confidence interval. You take a point estimate, a p-hat or an x-bar, and add and subtract a margin of error to that. We'll get into the actual calculations in a second, but this is its most basic format. And so if you see something like recent survey, 63% of those contacted say they plan to vote for candidate A, the scenario we saw earlier, margin of error is 3%. The confidence interval is going to be 0.63 plus or minus 0.03. And you've probably seen it written like this in that interval notation where you got the lower bound all the way to the upper bound. And that gives us our range of guesses for what we think will actually happen for the true proportion of all voters in the city who are similar to the ones in the sample that we took. Inference can't go beyond the sample the type of people in the sample you're looking at. So it can't be if I do 63% of people in the city A, I can't apply that to other cities. It has to just be applied there. So all the stuff you learned back in collecting data about representative samples still apply here when you're interpreting the confidence intervals. So look out for little tricks with that. And what I also hope you know is that those numbers, that 0.6 to the 0.66, actually don't necessarily have to be true. We don't know anything about what people are actually going to do when it comes time to vote, or if the results from our survey are actually accurate. It just gives us a range of guesses. So here's an example similar to a problem on the AP exam back in 2015. This was in the free response section. So we were given a scenario like this. Random sample of users of a social media site asked, have you ever put false information about yourself on your profile? Confidence interval for P constructed from the responses was listed as 0.31 to 0.41. I'm not giving a confidence level yet. We'll get into that in a little bit. But if you do want a confidence level, let's say it was a 95% confidence interval. First thing to figure out is what in that confidence interval, what was the point estimate and what was the margin of error? Should be maybe 15, 20 seconds to look at that and identify what there must have been for a p-hat and what there must have been for a margin of error to get that confidence interval. All right, Dara, my hint to you is you've got a lower boundary and an upper boundary. The point estimate, that p-hat, had to come right in the middle because the margin of error is built on either side. So if you can figure out what's right in the middle of that confidence interval, you know what that p-hat was. 0.365. 0.365. I think I'm going to get 0.36. Because if I find like average together the endpoints or do the median of the endpoints, yeah, I'm getting 0.36. Because the halfway point, okay, yeah, 0.36. That 5 might come up in another way, though. So that point estimate is 0.36. So where does the 5 come into play? Yeah, so specifically it's 0.05. We added and subtracted 5% from that margin of error. So what that means is in whatever survey we took, with however many people there were, 36% of the people in the survey said, yeah, I've put false information on my profile. That doesn't necessarily mean that 36% of all users have actually done that, just that 36% of users in the sample we took have done that. And then based on the sample size that we had, we were able to compute a margin of error. And we'll see later how to calculate that specific 5% figure, as well as we might come back to this later and work backwards from that margin of error to figure out how many people did they ask in the first place. And so with that, the confidence interval goes from 0.31 to 0.41. So I should believe any answer from 31% to 41% as valid. So if someone says 40% of our users say that they've done this, you'd be like, yep, checks out based on my sample. If they say only 25% of our users have done this, you'd say, I don't think so. My confidence interval says otherwise because 0.25 is not contained within that. I would reject that hypothesis. And so follow-up question, and this is the one that was similar to the free response question on the AP exam, is it reasonable to say that more than 1/3 of all users of the social media site have in fact put false information on the profile? Based on this interval, can we say that more than 1/3 of all users have put false information? And you can give me a yes, you can give me a no, you can give me a yes with a reason, a no with a reason, or just a guess. I think I got a question like this wrong on the test. Well, okay. If you're willing to take a stab at it, take a stab at it. Looks like we've got a couple more people joining us. If you're joining us live here, we have been discussing what a confidence interval represents before we're getting into how to actually calculate it. And we know that what a confidence interval does is it takes a result from a sample and puts that right in the middle of an interval and builds a margin of error on either side to give us a range of guesses. So in this example so far, we have been given that anywhere between 31 and 41% of users on a social media site say they've put false information about themselves on the profile. And now we're being asked if it's reasonable to say that for sure more than 1/3 of all users have put false information on their profile. So this would be no. No, it's not reasonable. Well, Dara, I hate to break it to you, but you are right. It is, in fact, no, not reasonable, because 0.33 is in the interval. This is where a lot of people get it wrong. They go, oh, 33%, that's reasonable. That's in the interval. So it has to be true that more than 33%. But the whole interval would have to be above 0.33 for me to justify, yes, it's more than 33%. Since 0.31 and 0.32 are reasonable guesses, it is still reasonable to say that it is possible that less than 1/3 of all users have put in false information. I think the actual AP problem, which we are not allowed to put in our presentations for legal reasons, had to do with like what percentage of customers receive a discount, and the number that they claimed was in the interval. And so even though the evidence looked like they were lying, since that number was still in the interval, we can't say for sure that the thing was malfunctioning or whatever. So it is not reasonable to say that more than 1/3 of users have put false information. The equivalent version of a hypothesis test would be if the null hypothesis was 0.33 and the alternative was greater than 0.33, since the entire interval is not greater than 0.33, I cannot reject that null hypothesis. It's still a plausible value. I can't say for sure that everything's above that. And so there's also a connection point between confidence intervals and hypothesis tests. And so before we get into the actual calculations, I'm going to run a simulation. I'm going to be switching screens here for a second, so just bear with me as the screens go. How do I do this? Close this video, and we're going to share a new tab. We are going to share this tab. Okay, and so what you should be seeing on your screen, is a number line basically from 0 to 1. And right now, we're going to do a simulation where we know that the actual population proportion is 0.5. So whatever situation you want to say about percentages, let's say it's 50% of people say yes to a certain question. Okay, and we're going to take some samples and look at a confidence interval that is constructed from the sample results to see if the confidence interval we get contains the correct answer of 0.5. You'll see this thing called confidence level is set at 95. The goal of this little activity here is to figure out what does that 95% confidence level represent. And so as I'm going to play with the slider, I'm going to make the sample size be 50, just kind of because I can. But if you think you know what that confidence level stands for, if you've already seen this stuff in your class, feel free to put a sentence or two down in the chat, and I can, as we go through it, we will look at what you said and see if it's what's coming up. If you're not sure, then this is the place for you. Because what we're going to do is we're going to take a sample from this population. And what you should see on your screen now is one sample popped up, and it says CI equals 0.560 plus or minus 0.14. That 0.560 is the p-hat, where in this sample, 56% of the people we got said yes. And then based on the sample size and what our p-hat was, the margin of error appears to be about 14%, 0.14. So the confidence interval would range, as you can see on the number line, anywhere from 42% all the way up to 70%. And I'm getting that by adding and subtracting. We're 95% sure the interval from, I can't read those numbers, captures the true population proportion of number. Okay. What you're interpreting, what you just typed out, is what we would say about the interval itself. I'm more wondering, what does the 95% actually tell us in general? So not interpret the confidence interval. You're right. Based on this confidence interval, we would be 95% sure that the interval from 0.42 all the way up to 0.7 would contain the true population proportion of people who said yes or whatever. And in fact, we can see that it does. 0.5 is in that interval. We're going into this simulation knowing that the answer is 0.5. Obviously, when you're doing this for real, you don't know if the answer is 0.5 or not. So you're just hoping that the answer is somewhere in there. That 95% confidence level has another specific meaning, though. And we're going to take a couple more samples. If we repeat this process 100 times, 95 out of the 100 different intervals would be captured in the true population portion of context. Jess, I like what you're saying. It's interesting. I would be careful with this 100 times thing, because just because it's 95% doesn't guarantee that it's going to be 95 out of 100. So I would say about 95 of the intervals would contain the true proportion. Or you can say something like, in the long run, if we were to repeat this process, about 95% would contain the true parameter. And let's do some more samples to see. So, oh, damn, that was, excuse me. That was sooner than I thought it would be. We just got a confidence interval that missed. So our p-hat was so low, 0.34, so far away from the true answer, that even with a margin of error, it didn't actually contain the correct answer. Now, I shouldn't expect that to happen a ton. Wow, this is happening. We've done 20 samples so far, and in 3 of them, our p-hats have been far enough away from the real population proportion that even with a margin of error, we're missing the real answer. And what you should see going down the line here is the p-hats are a little bit different every time. Most of the time, they're close enough to that population proportion that when you build out the little wings, the margin of error, and get the endpoints of your interval, it contains the correct population proportion. And to Jess's point, if I keep sampling, and I'm going to go all the way, I'm going to skip ahead, 25, 25, 25. All right, I have just done 100 samples in this situation. I've done 100 trials. My 95% confidence interval procedure actually only created 88 intervals that contained the correct answer out of 100. which is fewer than I expect. I did this simulation earlier today with one of my classes, and we weren't this low ever, actually, with 95%. In fact, if I keep going, you can see I'm now at 500 trials, and I'm over 90% accuracy. Eventually, in the long run, this is going to get closer and closer to 95% hit. 1,000 samples in, 921 of my intervals have contained the correct answer. So I'm getting closer to that actual capture rate, if you will. And that's what that confidence level stands for, is what percentage of all intervals created from this sample size, from this population, would contain the correct answer to the actual population proportion. And I'm guessing, a couple of you have done this before, what's going to happen if I increase the confidence level? So same sample size, increase the confidence level. What's going to change here? Are the intervals going to become wider? Are they going to become narrower? Yeah, bigger interval will be produced. It should make sense, and you'll actually literally see it happen. Is if I go up to 99%, I have to build out a wider margin of error to give myself a larger range of guesses to be more sure that I'm going to contain the correct answer. And of course, if I slide down the confidence level, you'll notice the margins of error are getting smaller. And if I go down to 80%, you'll see about 78% of my 1,000 samples have contained the correct answer. If I slide it up to 99%, all right, 98.2% have done it. So I'm pretty close to the advertised confidence levels in my 1,000 sample scenarios. And I'm guessing you also know what will happen if I crank up the sample size. What will happen to my confidence intervals when I increase my sample size from 50 to something bigger? I'm going to do that here in a second. Just says decrease. Well, if we think back to what we know from sampling, when I increase the sample size, the results of my samples became more consistent. So what I want you to do is just kind of like take a look at the screen right now and look at where the dots are compared to that 0.50. Look at how spread out they are from the 0.50. Some of them are right on the money. Some of them are way up in that 0.60 range. Some are way down in the 0.30 range. Some are in the 40s. I'm going to crank up the sample size to about 200. And I'm going to start taking some samples. I already got one that missed, you can see. But what I want you to notice is 20 samples in, my p-hats are almost exclusively, exactly, Dara, my p-hats are getting closer to the point estimate. Sorry, not close to the point estimate. The point estimates are getting closer to the true population parameter. The p-hats are getting closer to p on average, meaning the standard error, the standard deviation of p-hat has decreased. Sample size goes up, standard error goes down. What that means for margin of error is I don't need to build as wide of a net. I don't need to cast as wide of a range of guesses to be as confident that I'm going to contain the correct answer within it. So since the results of p-hats become more consistent when the sample size goes up, to have 95% of my intervals contain the correct answer, I don't need to go out as wide as I used to. And there's a really good reason why the margins of error right now, when I click on the different confidence intervals, I know it probably is really small on your screens. They're pretty much all 0.07. Now, the last time I did this with a sample size of 50, they were mostly all 0.14, 0.14, 0.13. So 4 times the sample size results in half the margin of error. And there's a really good reason for that algebraically. And if you know what the formulas look like, you'll probably know why that is. But when we do look at the formulas later, if you don't know why it is, you will see, and then you'll be like, whoa, he made a connection for me, and I feel smarter now. So what I hope we've seen at this point, and what I'll do one more scenario here. Let me reset this. I can reset the population proportion to be anything else. So let me go to like 0.35. So now the green line's at 0.35. I start taking samples. My p-hats should be close to 0.35. They won't all be close to 0.35, but they should be. And so still, when I build out my confidence intervals with my 95% confidence level, I should have about 95% of the intervals built from samples of size 200 using this procedure. 95% of them should contain 0.35 as the correct answer. And this simulation, we knew what P was. But remember, when we're doing it for real, I don't know what P is, which is why we have to give the whole range of guesses. And we can't say for sure if any of the specific numbers in the interval are right or not. We just go, we are 95% sure that the real answer is somewhere between and here, endpoints of the interval. So I'm hoping that by seeing that, we know a couple of things about confidence intervals, namely that point estimates are meant to be our guess at the actual parameter. And then we build a margin of error on either side to give us some wiggle room to actually capture the correct answer. The confidence level describes what percentage of all confidence intervals we could build would actually capture the correct population parameter. If I increase the confidence level, confidence intervals get wider. If I increase the sample size, confidence interval gets narrower because the samples themselves get more consistent. And of course, the opposite is true. Smaller samples create a larger margin of error, and a lower confidence level will create a smaller confidence interval because you don't care about as many intervals hitting the correct answer. So with that in mind, we're going to transition back to the actual main PowerPoint, and we're going to talk about how to actually calculate and put together the margin of error and start looking at some practice scenarios. I have to change my little screen though. So we're going to do close video, share screen, and you're going to share this, and we are going to come back here. So looking at that picture on the side there now, I'm hoping that we have a pretty good feeling of what it represents and what it is. Let's actually dig into constructing a margin of error. So we know that a confidence interval is a point estimate plus or minus a margin of error. Well, on your formula sheet for the AP Stats exam, it actually says this. It says confidence interval equals statistic plus or minus critical value times standard error of statistic. So in the case of proportions, the statistic is the point estimate, p hat is the point estimate, and the margin of error comes from a critical value times standard error of statistic. I wonder, what the heck is a critical value? What the heck is a standard error? Okay, let's pause for a second. Standard error of statistic, we've seen that before when we did sampling distributions. You probably recognize this formula. But in the context of margins of error and in confidence intervals, we don't actually know what P is. Like on the simulation, we saw P was 0.5 or P was 0.35 or P was 0.7. When you go to actually take a survey and try to estimate what proportion of all people are doing something or saying something or agreeing with something, you don't know what it is before you start. So the best that you can do is use p hat to estimate P. So also on the formula sheet, you will see this. Instead of a sigma, instead of that standard deviation symbol, you're going to see an S to represent that he's coming from a sample. So instead of the standard deviation of p hats, it's called the standard error of p hats because it's an estimate of the standard deviation of the sampling distribution based on the specific statistic you get. Not really much of a change here, just using p hats instead of P. The one way I could see that they might try to trick you with this is if they give you a scenario where you do know P, then to calculate the standard error, you're going to use the formula at the top, not the one with p hats. If you don't know P, you're going to use the formula at the bottom where you actually use your p hat. And so statistic is p hat, standard error of statistic is that, and a critical value is a thing called a z-star. A z-star will depend on your confidence level. And the bigger your confidence level, you might be guessing, the bigger your z-star is. We saw on the simulation that the confidence level represents how confident we want to be that our interval contains the actual value of P. The most common confidence levels are 90, 95, and 99. And we know that it's a capture rate. So in repeated trials of sample size, whatever, blank percent of the intervals will contain the true population proportion, population mean, whatever. Okay. But the reason it's called a z-star is because sampling distributions, when we do it right, have this shape, a nice normal distribution. And with a nice normal distribution, we have z-scores. And so what the z-star is figuring out what z-score I need to be at above and below 0, above and below the mean, above and below whatever p is supposed to be, to ensure that that percentage of samples would actually have a confidence interval that contains the correct answer. Long story short, you should memorize these three numbers: 1.645, 1.96, 2.576. You're probably using them enough anyway that you've seen them enough times and gotten used to them. But if you're ever unsure of what a z-star is, you go to table B in the back of the AP Stats exam. It's called the t-distribution. We'll talk about t-stars next week when we do confidence intervals for mean. And you can see at the bottom, it has a bunch of confidence levels listed and a bunch of numbers right above those percentages. Those are called your critical values. So to ensure that 95% of all samples would contain the correct population proportion, we should use 1.96 times the standard error, and that will shade in 95% of the inside of that bell curve. And you might remember back from first semester, 68, 95, 99.7, your teachers might have told you that. 68% of all individuals in a normal distribution are within 1 deviation of the mean, and 95% within 2. Okay, we actually lied. It's 1.96 deviations to have 95%, not 2. So I hope you can forgive us for slightly rounding it the first time we did it. And you'll see that 99, you might remember 99.7. If you look at 99.5 and 99.8, 3 would fall right in between that. So these are quite literally just z-scores, the number of standard deviations, their standard errors away from the mean. And what's nice about this little table at the bottom is it's going to come in handy quite a bit when you are doing multiple choice problems and you are looking to actually put together a confidence interval. In the multiple choice section, the most common thing to do is to give you a scenario and then actually give you a setup of a formula to say, like, which of these intervals represents the 95% confidence interval for whatever. So like in this scenario, in a random sample of 251 students in a large school district, 107 say that they would prefer to start and end the school day 1 hour later in the day. I'd vote for that too. Which of the following represents a 95% confidence interval for the portion of all students in the district who would say they prefer to start and end school 1 hour later in the day? And then they give you a bunch of answers like this. So they're not asking you to get the endpoints of the interval. They're not asking you to come up with any specific numbers. They are asking you to pick out which of these setups does it the right way. And the first thing I tell my students to do is look for what the confidence level is and look at what the z-star would be for that confidence level. And you can immediately cross out anything that doesn't contain that specific z-star. So in this scenario, I see 95% confidence interval, meaning 95% confidence level, meaning I know my critical value has to be something very specific that I see a bunch. And I will pause here before I circle the correct answer and give you folks who are here live a chance to answer this one. See what you think. And I put the formula at the top of the page because you have access to it on your formula sheet. If you're ever asked for a confidence interval, you'll see the thing written out in words at the top of the page. And then there's a whole table of symbols and formulas and stuff that you could put together. So just says B. Just says B. Jess, what's wrong with D? D looks really similar to B. Oh, Dara, you don't see anything. Dara, are you watching? So if you, I know I can, just obviously you can see something. Dara, I'm sorry you're not seeing anything right now. I'm not quite sure what to do on your end. If you're watching on a phone, or I'm wondering if my screen's cut off, if the size doesn't line up, I'll definitely reach out to like Fiveable HQ after this to see what's going on. You might just need to refresh. And Dara, if you might have to like exit and come back in, and hopefully something will clear up. But I've got a few choices listed here. A says 107 plus or minus 0.95. So A and C are knocked out because that 0.95 is not the right critical value. And it's 251, not the 107 who wanted to start school later. Yep, Jess, that's exactly it. It's the wrong sample size. N is the sample size, not the number of successes in the sample. So that 0.426 comes from 107 divided by 251. Okay, never mind, it's working now. So yay, Dara, welcome back. Well, spoiler alert, it turns out that, clicking the wrong thing, B as in boy is in fact the correct answer from this scenario. And in my experience, there is at least one multiple choice question pretty much every year out of the 40 that is this almost exact same setup, where they'll give you a one sample Z interval and they want you to pick out which one is the right setup. And it's one of those things where, like, at first students kind of freak out about seeing all these symbols and formulas and plus and minuses, and then they realize, oh wait, this is actually like the gimme question, because all I got to do is pick out the confidence interval level, look up the right Z star, cross out the ones that don't have the right Z star, and then just piece together the other components of the formula. And the reason that they set it up like this is because the fine folks at the College Board know that if you have one of these bad boys, one of these TI-84s, you could take the information they give you and pop in like 3 buttons and spit out the endpoints of a confidence interval. And so what they're testing your knowledge is what actually is your calculator doing to get those endpoints, to see if you know how to set it up by hand. And so where you can use the calculator, though, is in a free response setting, right? You probably about once every other year, maybe once every 2 to 3 years, we are asked just specifically construct and interpret a % confidence interval for something. Back in 2017, there was a confidence interval for a proportion. In 2019, last year, part of the question 6, part of the investigative task, was building a confidence interval piece by piece, and you ended up with a 96% confidence interval. So there's a somewhat decent chance that we'll be asked to make one this year. Could be a proportion, could be a mean, it's not really sure. But remember, you got to do all these things. You have to check the conditions. Every time you're doing a confidence interval or running a hypothesis test, you have to check the conditions. Okay. In the case of proportions, or in the case of anything really, got to cite where you're told the sample or samples are random. And if it's a 2-sample difference of proportions, you have to make it clear that the samples were independent of each other. So not just randomly selected, but independently randomly selected. Okay, and then there's a second condition. And before I reveal it, folks who are here looking for a review, what is that second condition that you have to cite? So not just that the samples are random, but something else about those samples has to be true. Remember, we're specifically normal or 10%. The one you have to check specifically on the AP exam, Dara, is the normal condition. The 10% condition, rubrics in years past have not explicitly asked for people to check the 10% condition. It's one of those, like, it's nice if you do, but you can get an E from checking just randomness and normal. But in the case of proportions, what do we mean by normal? What does it take to be normal? There's a special thing that has to be true. Successes and failures have to be 10 and more. Or the counts, yeah. Dara, your teacher did an excellent job, because you are exactly right. Okay, so what we mean by normal is ensuring that the sampling distribution of p hat is normal. And the way to ensure the sampling distribution is normal is that we would be expected to have at least 10 successes and at least 10 failures. In the case of an actual sample, if we actually have at least 10 successes and at least 10 failures, then it's reasonable to assume that other samples of similar size from the same population would also contain at least 10 successes and at least 10 failures, and the sampling distribution would be normal. And then all the calculations that are based on the normal distribution are valid, and our answers are going to be good. So you have to check those two things. The random one is super easy. The one but normals, you can call it large counts, you can call it large samples, you can call it normal condition. Any of those three names are good to go. They're seen as equivalent. Okay, you then have to name what the interval is that you're doing. Okay, if your teacher is like me and you use TI calculators, he or she is going to get very upset if you say 1 prop z int, because that is not a name, that is just a calculator label. What we are doing if you are building a confidence interval for a single population proportion is you are building a 1 sample z interval for a population proportion. Right? Name that whole thing, or you can write out the formula. I encourage students to write out the name, because if you misplace a hat or an N or a Z or a T or any of your symbols is off, it's like you didn't name it at all. Using a wrong symbol completely eliminates your correct naming of the interval. So come up with the names like 1 sample Z interval for a population proportion, 2 sample Z interval for a difference of population proportions, 1 sample T interval for population mean, 2 sample T intervals for population mean, or sometimes the matched pairs T interval for a difference in population means. We'll do with those next week, but specifically name the number of samples, and it's Z or T. Z is for proportions, T is for means. And it's important to have the word population in there because the interval is to estimate what's going on about the population. Once you've named it, that's where we can either crank out the calculations by hand or go to our handy calculator and go to stats, tests, and scroll down until you see the appropriate label of 1 prop z int in my case. You don't have to show any algebra if you do it in the calculator. And then this is where we write that sentence star that you wrote way earlier with the, we are 95% confident that the true population proportion is between, and when you're doing this, it's a really good idea to just copy and paste. Okay, wait, sorry, I don't get why we're not using the 10% independent condition. It's a good question. So here at Fiveable, we are interested in getting you your scores on the AP exam. And having gone through the rubrics of the free response section of the last several years, anytime there actually is a hypothesis test or confidence interval, your point on the conditions part is not dependent on you checking the 10% condition. It is dependent on you checking whether the sample was random and independent and whether it was large enough. In your own class, sometimes teachers are a little more sticklers with like, what if it failed the 10%? So the good news is scenarios you get, will this be the NPNQ? Just NPNQ is the 10 successes and 10 failures. That's the large samples. We are checking that every time. What Dara is referring to with the 10% condition is when we're sampling in real life, we sample without replacement. And when we sample without replacement, for every success we get, we are now changing the probability of a future success, like back with conditional probability and binomial stuff. However, when the population size is big enough, and you take someone out of the population, and I go from 10,000 out of 20,000 to 9,999 out of 19,999, the difference in probabilities there is so negligible that it's like it's independent, even though it technically isn't. Dar, the good news is no free response scenario, quite literally, that I've ever seen where you're actually asked to construct the interval or run the hypothesis test has actually failed conditions. The only scenarios that have failed conditions on a free response test, free response question that I've seen have been ones where you're explicitly asked which condition is not met, or explain why you can't run this test, or explain why this is a bad idea, or whatever else. And in those cases, it's almost always the fact that the sample itself was biased because it was non-random, or it was a super duper small sample and it was like 3 successes and 17 failures or something. And so it didn't quite match up. So Dar, to answer your question, to put a stamp on it. Yes, you should check the 10% condition, and we should do things like, it's reasonable to say that the population is at least this size, but you're not really explicitly needing to do that on the AP exam. So do it in your class, but know when you get to the AP test, if you're in the habit of doing it, keep doing it. But in terms of actually needing to do it, we don't need, quote unquote, to do it. With that said, now that we know the things that we have to do to earn the point, and usually 1 and 2 are combined together. Usually it's like, did you check it's random? Did you check it's normal? Did you name it? And those 3 things get you an E. And if you do 2 of those things, you get a P for partial. The confidence interval is its own answer, and then the interpretation is its own answer. Let's do one. A city manager has been receiving complaints about people illegally parking on busy streets by leaving their cars parked for a longer time than they are supposed to. A randomly selected parking spot is chosen and observed for several days. Out of 80 cars that park, 23 stayed for longer than they were supposed to. Construct and interpret a 95% confidence interval for the proportion of all drivers that would park their cars in that spot longer than they are supposed to. Let's do these things on the side. If you don't have a calculator handy, feel free to just kind of set up the initial stuff and then write the sentence with some blanks in it. If you do have a calculator handy, I would actually run this interval and actually do the play if you have a chance to do it. Oh no. We have class sets at my school, and like all of the calculators were dying at the same time. And so we had to do like a mass order of batteries. And we got this like giant Amazon package of like 300 batteries. And we had like a calculator party where we changed out all the batteries because kids were getting really mad at me because they were not working. So I feel you. But you can definitely check the conditions and make sure that this does match everything it's supposed to. Oh no. Oh, that's bad. Yeah, I don't know what I'd do in that case. We're back in the Stone Ages. We're back with the 84s. You got to retake. Okay, good news. You got to retake it. I guess your teacher knew you didn't do it on purpose. You're the kind of student that would. That'd be pretty slick though if you knew you weren't ready and you just forgot to charge it up and oh no, I can't do any of the math now. Guess you have to give it to me another time. That's okay. See, someone's gonna walk away from this and be like, what'd you learn from your Fiveable stream? I learned how to cheat in my class. No, that's not what we're learning. We are learning how to interpret confidence intervals. If you're watching on replay, I do not condone leaving your calculators uncharged when you're supposed to need them. That is not the position of Fiveable. All views are my own. Well, you know what? You came to the right place, Dara. You've oh yeah, Mafuz, welcome. You are a little bit late, but that's okay. We're gonna do after this one. Actually, I'm gonna kind of do a recap, and I'll stick around for a few minutes if you have some specific questions about confidence intervals. Just for the sake of time, for the people who are watching on replay, in this situation, we have been asked to construct and interpret a 95% confidence interval for the proportion of all drivers that would park their cars in that spot longer than they are supposed to. As soon as you see the word proportion, good news, it is a Z interval. You see the word mean, it is a T interval. So we have to check our conditions. With proportions, with anything, we got to make sure it's random. They mentioned that the parking spot was randomly selected, and then we observed what was going on. So that has been met. And with proportions, we were supposed to have at least 10 successes and at least 10 failures. And since 23 of the cars stayed longer than they're supposed to, the other 57 out of 80 did not. Both of those are larger than 10, so the sampling distribution of p hat is normal. I actually just realized that I myself on this slide would get a P for this because I did not explicitly compare those numbers to the number 10. I did a bad job there. I should have 23 and 57, and I should have both of them greater than or equal to 10 to communicate to the reader that I knew that 10 was the magic number. Because if you've already done t-tests or t-intervals, you know that 30 is the magic number, so that wouldn't have counted. The B condition, yes, NP, NQ. That is correct, Jess. In the case where we actually already have the sample, NP would be 23 and NQ is 57. So it's NP hat and NQ hat in that case. So if you calculate P hat, 23 out of 80, and then multiply by 80, you get 23. So that second one, NP and NQ, were both greater than 10. And that is the large counts or the normal condition. Both of those are checked. We're going to name the interval. In this scenario, there was a single sample of cars. So this is a one sample. It was for a proportion, so it is a Z interval. And since it was for a proportion, this is a one sample Z interval for a population proportion. You can get more specific here and say for the population proportion of all drivers that would park their cars in that spot longer than they were supposed to. But we're going to say that in our sentence at the end. We're going to write down the confidence interval. I go to my calculator. I go to stat tests. I slide down to one samp or one prop Z int when I'm doing proportions on the, if you have a TI calculator, they're called one prop, not one samp. One prop Z int. I say X is 23. I say N is 80. I say my C level is 0.95, and I click calculate, and it spits out something like that. I'm rounding to the nearest thousandth, as I always do on the AP exam. If you include extra points after this, if you go to the 10,000th place or the 100,000th place, also fine. But if you go 0.188 to 0.387, that is considered accurate enough. And then my sentence, because it was a 95% confidence interval, I say that we are, in fact, 95% confident that the true proportion of all drivers that would park their car in that spot longer than they're supposed to is between 0.188 and 0.387. So then if we get follow-up questions about the city believes that it should, it should make a new law if more than 15% of all people are doing this. Based on this interval, we have evidence that more than 15% are doing it because the entire interval is above 0.15. But if they wanted to make the law when more than a quarter of people are doing it, well, I don't have evidence that more than a quarter of people are doing it because there are numbers less than 0.25 in that interval. If they ask us to say, like, for every person that gets a ticket, the city will make $100 in revenue, we could multiply those endpoints by 100 to represent the number of dollars that the city would expect to get in a sample of 80 cars. Something like that. Kind of thing. Not much else is done with actual construct and interpret. Typically, those are standalone questions with multiple scoring components. So if you do see one of these, get excited because it's pretty procedural. And once you do it, you are like racking up the E's, which is a good time. So at this point, we have reminded ourselves of what a confidence interval is, both in words and in symbols, specifically for p-hat. There are some other things that come up sometimes. Sometimes you are specifically asked to solve for n to get a specific margin of error. And so that involves some algebra. We also could do two sample intervals for the difference of proportions, but you pretty much end up running it the same way. It's just now instead of a single p-hat, it'll be a p-hat 2 minus p-hat 1 or a p-hat A minus p-hat B or something like that. And then the standard error gets a little bit bulkier with N1 and N2. But the general setup is very, very similar. And so both multiple choice and free response, you're doing pretty much the same thing, but now inputting two sets of numbers instead of just one number. A lot of those cases will be two different groups versus each other or passage of time. So compare last year, this year, compare men versus women, compare control versus experimental group, and compare if there's a difference in whatever proportions you're looking at. Dara, you were saying you're just getting into that now. So the good news is if you know the basics from this stream, when you get to the two sample Z intervals, you're just basically running this all back with a couple of little tiny extra things that really don't change your procedure very much. And next time we're running up on time here. We're going to dig into confidence intervals for means, T intervals, two sample hypotheses. And what I love when I do two sample hypothesis tests or like two sample intervals is like once you've done the one sample stuff, the two sample stuff usually flows pretty well. It's not really that much harder because it's a very similar procedure. So at this point of the year, we are like going to start here at 5able, like getting into, I just understand what pooling was. You know what? I don't really understand what pooling is either. Like real talk, it has to do with whether or not you're going to consider the samples having come from like, I think at the same time or not. I'll have to look that up because honestly, the AP exam doesn't really get into that. All right, well, I should brush up on that myself because that is actually not a thing I emphasize in my class. We just know that we say nope, 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 and keep it rolling. All right. Like I mentioned, at this point we are up on an hour. I want to respect folks' time. I will stick around for a few more minutes. If you want to get another example scenario, or if you want to ask for the multiplying symbol. It is a multiplication, but the asterisk is a special thing to indicate that what you're getting, that critical value, is a special z-score. And I will go back to that slide in a minute to show you what they're talking about. But the asterisk does represent, it's a special symbol for a critical value. It also happens to be multiplied to that standard error. So coming back, where is it? It's the next slide. So that critical value, that thing called a z-star, is specifically having to do with how far away, like what z-score would I need to go to ensure that whatever my confidence level is, 90%, 95%, 99%, contains that many samples that will capture the correct answer. I'm saying a lot of things that if you weren't here earlier probably don't make sense, so I do apologize. But at the end of the day, all of these little asterisk symbols, those z-stars, are found at the bottom of a table that is in your formula sheet when you're actually taking tests. So there's a table called Table B on the AP Stats exam. It's a T distribution. At the bottom of that is where you get all of the z-stars from. And what's great is it helps you when you're like going through different multiple choice scenarios and trying to eliminate answers. Knowing which z-star goes with which confidence level is a really easy way to start eliminating answers off the bat. Thank you guys so much for being here.